We can start the second session, laser ranging application for precise orbit determination. This is the last talk of the morning. It will be by Julian Zeitlhöfler. We'll speak about a comparison of different ocean's tide models.
Okay. Hello, everybody. Thank you for the introduction. My name is Julian Zeitlhöfler, as said, and I will give a talk about a small comparison of ocean tides models. Let me first introduce the topic to you. Though ocean tides are very important for a lot of geophysical applications, such as precise orbit determination, or satellite gravimetry, or for coastal floodings to study how the effects are due to the flooding event, or for solid earth geophysics. And those corrections, or those tidal effects, are used as corrections to a lot of space geodetic observations, such as SLR. And those corrections are then added as a model, in our case a barotrophic model, to the observations. The ocean tide models are also used as a reduction of aliased noise, so, let's say like this. And due to this, in the past, there were developed a lot of models which are sometimes based on previous models, which are enhanced, or which are empirically developed. Now we are talking about SLR here, of course, and why are those models important for us? In the picture, you can see an SLR station on the ground, which is affected due to ocean tides in the height component and also in the position component. And it's due to the loading effect of the water in the oceans. And the satellites, both spherical and non-spherical satellites, are affected by mainly gravitational effects which are caused by the tides. And both in POD have to be accounted. In my comparison, I used three models. These are the Empirical Ocean Tide Model 11A, EUT11A, the Finite Element Solution 2014C, and the EUT20 model recently published by our institute. And this slide should give you an impression of how different the models are. They have different numbers of main tides, 18, 34, and 19. And also, if those two models have 18 and 19, it does not mean that these 18s are taken with an addition of one more, but there are different compositions of main tides. At the DGFI, we are using additional atmospheric tides, S1 and S2, which are then added to the S1 and S2, which are contained in the ocean model. Let me talk about the settings of my investigations. I used three satellites. It's Topics Poseidon, which is a non-spherical satellite, Laris and Lachios, which are spherical satellites. And I used different intervals of time span. Topics Poseidon flew from 1992 until 2005. And Laris and Lachios data is provided in my investigation from 2018 until 2020, mid-2022. And you can clearly see already that they fly in completely different heights, from 1,300 to over 5,000 kilometers. And I wanted to know which effects are due to the model to the satellites in different heights. The topics Poseidon orbits, the arcs were computed in 3.5 days, and the other two satellites have orbit arcs of 7 days. I also applied 0.01 sigma to the parameters to not absorb any effects caused by the ocean tides models in those parameters. I also estimated station coordinates in all three satellites, and then I had first a look at the empirical accelerations of these orbits. Here you can see now the empirical accelerations of the topics Poseidon orbit. In the top left, I show the transverse cosine. In the top middle, the transverse sine. And in the bottom line, the normal sine, normal cosine, sorry, normal sine, and a normal polygon. A polygon means that each empirical acceleration value is estimated each 12 hours. And cosine and sine value is estimated once per arc. And here I'm showing the differences between EOT20, FES 2014, and EOT11A. Though if we have positive values, it means that the new model or the first model, which is given in the legend, has larger values than the second one. And we can see here that in most cases, the values are positive. That means the EOT11A model fits better to the observations. Here are now the comparisons of Laris parameters. And here we can see a mixed picture of the values. The first value is the value itself, though the absolute values, and the second part here is the sigma, so the standard deviation of the parameter. And here we have sometimes a better result in the EOT20 or FES 2014 C model. The results for LarGS1 show similar results or values, and don't be confused, here is nothing shown. It's so small that it cannot be shown here in this plot. The order is 10 to the power of minus 14, and if we are considering differences here, then they are up to 1 or 2 orders smaller than the actual values. In case of the sigmas of the standard deviation, the standard deviations, they are up to 2 orders smaller than the initial values itself. I also wanted to look at other parameters which are estimated in the POD, such as the atmospheric drag scale factor. I chose the satellite Laris, and I had a look at the frequencies contained in that parameter. The main information is that I get a strong signal at 67 days, at 2 weeks, 14 days, and the unique feature in this plot is that there is only a signal of 9 days and 30 days for EOT20. The others do not have that. The middle plot is of the satellite LarGS1, and I show the albedo scale factor. And in this plot, I can see a clearly one annual signal. The other periods are mixed. Sometimes EOT20, L1A, or FES has better results, though I cannot say it's a clear, better model in each of the cases. For the satellite topics Poseidon, I can see a clearly annual signal and a signal of 170 days. And some of you might know that it's the draconitic period of the satellite. It's a very characteristic period, and it's related to the orbital parameters of the satellite. But as I already said, I cannot say because of those investigations that this model or that model is better than the others or outperforms the other models. As a conclusion, I can say that these the ocean tides in general have to be considered when dealing with SLR data or other space geodetic data, and they affect both the station and the satellite. And the comparisons of those models based on 3 satellites show that they are comparable, and this is also a good result because this means that the application or the usage of any of these 3 of the ACs can be used or is good also to cross-validate the models or to have different impressions of different models. The special thing about the EUT-20 is that this model is specially improved in coastal regions. It's to communication to a colleague of mine. And the satellite is mostly flying over open ocean, and this model does not contain so much variety compared to EUT-11A. An outlook could be that I include the GOT-410C model into the comparison and see how this model is compared to the other. If you have any questions, feel free to ask, and thank you for your attention.
Thank you, Julian. Are there any questions from the audience?
If I remember correctly, you made some comparisons of open height models. The differences in global maps are often quite local. So I would guess that it would be a better way of comparing to look at station residuals close to these areas where you have differences instead of looking at all the things that are global, just a plan.
Thank you. Should I repeat? Yes, okay.
Sorry, what? No problem.
Sorry.
Yes, that would be a further step, to look at specific sites which are close to the ocean and to get an impression of how, for example, the station Brest, close to the sea, is affected by those ocean tides, or the effects which are obtained by the models. Thank you for the point.
Other questions? We have a comment from online. I would recommend to add Starlet to your analysis. It was a satellite designed to be sensitive to tidal perturbations. From Frank Lemoine.
Sorry, which satellite was it?
Sorry.
Which satellite?
Starlet.
Starlet, okay.
Yes.
Thank you.
Other comments or questions? Okay, this was the last presentation of the morning. We are perfectly on time. So we can have lunch, and we will start again at 14:30. Thank you.